Okay, so let's look at some of the practice problems from section 9.2. So we have a 0.44 meter length of rope. It has one fixed end and one free end. So we want to make sure we highlight those types of things as we go through the problem. So we have fixed and a free. So we are working with that type of expression. A wave moves along the rope at a speed of 350 meters per second with a frequency of 200 hertz and n equals 1. Okay, so we would also potentially need these expressions right here. So what is L1 if the frequency is doubled? Okay, so what you could do is you could take the original, or take the expression, put L1, 2 times 1 minus 1 all over 4, and then instead of lambda we could replace it with velocity over frequency, and our velocity is 350. Our frequency has been doubled, so it's not 200, it'll be 400. And if you punch that in, so you'd have 350 divided by 400 divided by 4, that's the 1/4 out front, and you would get your 0.22 meters. Okay, so that's sort of the mathematical, just calculating way. You could also approach this problem a little differently. You could also look at, if you just took this expression right here, and if you doubled the frequency, the only way for it to maintain equality is if you half the other side. Okay, that's a little more sophisticated way of approaching it. So by doubling the frequency, you're actually halving the right-hand side. To maintain your equalness, you'd have to half the left-hand side, which means instead of 0.44 meters, you'd have 0.22 meters. That's a little bit more of a sophisticated way, but it's another way of looking at the problem. What is the length of the string? Let's see if I can get rid of all this first. What is the length of the string if n equals 3? Okay, and again, you could try a little bit more of a sophisticated approach. We're just going to try punching in the numbers first to see what happens. So what is the length of the string? So we're looking for L. So we're trying to find L3, or the third harmonic. So we would have 2 times 3 minus 1 over 4. Okay, and then again we would still have, and I'm going to assume we're going back to the original question and not keeping that frequency doubled, but we'll see what happens. So our frequency at the original was 200. Okay, so that's not the best wording, but let's take a quick look. So we have 6 minus 1, so 5/4 out front, timesing that by 350 and dividing it by 200, and 2.2. Okay, so that was correct assumption. So we would need a length that's a length of rope that's 2.2 meters in length, being agitated at a frequency of 200 hertz. And if we had that, we would create the third harmonic. So if you imagine from a picture standpoint, here's our rope, and if we did fixed free and we want the third harmonic, so one of the reasons I had you draw the pictures, so that would be first harmonic, second harmonic, and then the one we want, third harmonic. Okay, so sometimes it's easier to reference the picture, sometimes it's just easier to draw it. Okay, so the third harmonic here would have 1 and 1/4 wavelength, or 5/4 wavelengths, which isn't a big surprise because we have that 5/4. This whole term right here is 5/4. And remember, this whole term here is just another way of saying wavelength. Okay, so the blue one here would be 5/4 or 1 1/4 wavelength. Okay, so making those connections is kind of important as you go through problems. Try not to leave anything a mystery. Try and link things as much as you can. It'll make future problems a little easier to solve. So what is L1 if the speed of the wave on the string is reduced to 200 meters per second? So again, we can punch in some numbers. So we want L1, the length of our rope. So we're going to have 1/4 out front. I'm just going to save the 2n minus 1, writing that down. We're going to change our velocity down to 200. And we're going to keep our frequency the same as 200. So we will have 0.25 meters. Cool. Okay, let's try the second one. The speed of a wave traveling along a 0.65 meter guitar string is 206 meters per second at n equals 6. So the sixth harmonic. The frequency is 950 hertz. So that's a fairly high frequency, so you'd expect this sound to be a little more high pitched. So what is the frequency if a string with a wave speed of 150 meters per second is used? Okay, so remember back a lesson or two we talked about wave speed of a guitar string was related to the linear density and the tension in the string. So those are ways you can change the speed of a wave in a guitar string. So let's go after number one here. We'll get rid of that. Okay, so what is the frequency if a string with a wave speed of 100? So now the other part I did mention is guitar string means we're automatically into fixed. Okay, that's an assumption that you'll need to know. Okay, so let's give this a whirl. So frequency if a wave speed of 150 meters is used on the sixth harmonic. And it's a 0.65 meter guitar string, so that's a fixed amount. So we could take 0.65 as our length. We have a sixth harmonic as my n value. All of that's over 2. And then my velocity is 150 meters, and my frequency is my unknown. Okay, so I could do a little bit of calculation here beforehand for those people who want to go through it. It would look something like this. I'd leave the left side alone. 6 divided by 2 is 3. 3 times 150 is 450, and that f, or frequency, stays on the bottom. Don't magically make it jump to the top. Multiply both sides by f. Divide both sides by 0.65. So we're rearranging that expression. Okay, and our frequency should be 450 divided by 0.65 and about 690 hertz, which is what we had written up above. Okay, and then second part, what is the frequency if the string is tightened to make the wave speed 350 meters per second? Okay, so all of those things are the same with the exception that instead of 150 meters, we're going to use 350 meters. So I'm going to be a little bit lazy here and change this. So that would be 3 times 350. We'll just change this throughout the problem and trickle it through. 3, 9, 10, 50. And then, will that work? Nope. Let's see, that's just 1050. I'll write over it. Okay, so 1050 divided by 0.65 and 1615. So let's just get rid of this guy. They probably rounded that off to 1620, I'm sure. We'll just write it as 1615 for now, and if we pop back up, well, 1600, they rounded off even a little bit more. So spot on though, that's how we attack that problem. Okay, last problem of that practice set, a string fixed at both ends. So right away we know we're into that expression. That's a length of 1 meter with a frequency of 44 kilohertz. Kilohertz, that's 44,000 hertz right here. That's an important one to make sure we know. Okay, it's also the fourth overtone, which is n equals 4. Okay, so which harmonics will be audible to the human ear? So the human ear can hear between 20 hertz to 20,000 hertz. Okay, so now if we take this, there's a connection here. If n equals 4, and I'm going to review this in the next slide because that might not be super obvious. But for a fixed wave, okay, the n values and the frequencies, they're all linked back to the fundamental. So if you were to look here, and we looked at this once with the Slinky demo already, the fundamental frequency will be this number down here, and all of these other frequencies have to be an integer multiplier of it. So if it's an integer multiplier of it, to get to 44,000 and n is 4, that means my fundamental frequency had to be 11,000 hertz. Okay, which means that at n equals 2, I have 22,000 hertz. And at n equals 3, I would have 33,000 hertz. Okay, so out of all of them, the ones we might be able to hear more than likely would be these two. Okay, so the first are fundamental for sure, maybe the second, depending how good your hearing is, but the third and fourth would be outside our range. Okay, so let's try tying it all together, and we'll use a guitar string fixed, which is our most common discussion point because most people have seen a guitar string or a violin string or something. So we're going to look at two quick cases. Case one is the fixed length of the medium, so the guitar string. So if we just leave the guitar string alone, okay, so there are a couple things we're going to highlight. So if we leave the guitar string alone, the linear density and the tension will be constant, which means the velocity is constant. Okay, and that's a really important idea. So that means that the speed of the waves in that guitar string is fixed. So any changes to frequency will change the wavelength, and any change to wavelength will change the frequency. Okay, so when you're looking at the velocity being constant, you can look at your universal wave equation, and that v value there is constant. So that means to maintain that constant value, if your frequency goes up, that means your wavelength has to go down. Okay, and vice versa. So if your frequency went down, then your wavelength has to go up. And those two will balance off each other, but the velocity will have to stay the same within that medium. Okay, so if you take a look at the expression, I've got my fixed expression here. Instead of lambda, I've put in velocity over frequency. And if we just take a quick highlighter here and we highlight all of the things that are constant. So we're saying we have a fixed length of a guitar string. So this guy is constant. We have a 2 that's constant. We have a v that's constant. And what we're left with are two variables, two pieces of information that can relate to each other. So now if I multiplied both sides by f, and I rearrange this expression, it doesn't really matter where all the other letters are. Okay, so I could have the ln there, it doesn't matter. V over 2n. Because these ones here are constant, it breaks down to being a proportionality question. So frequency is proportional to the n number. So if my fundamental frequency on that string when I first agitated the string, I would get that first shape or standing wave at n equals 1, and if it vibrated at 100 hertz, then my second harmonic, my n equals 2 value, would be twice as much. So if I doubled the frequency or I doubled the n value, then those two numbers are going to grow together. Okay, so then if I was to do this one here, n equals 2, okay, I would have my second shape, which is the full wavelength, and you can carry on drawing the rest of the pictures, but if n equals 3, this would be 300 hertz, and this would be 400 hertz for n equals 4, and you can see those are all integer numbers because of this proportionality. Okay, and again, this is for fixed. Let's take one more look here. So case 2, if I change the length of the medium, the guitar string, and this is more realistic for how you play a guitar. So you can play an open string and you'll hear a sound, but then you put your finger down on the fret and it changes the length of the string. Okay, so again, I've taken those same expression, but I'm holding some other things constant. So I'm going to hold n equals 1 as constant. So we're just going to look for the fundamental frequency of each string. That's normally the loudest note. Okay, there are other frequencies that fill in. If we get a chance, we'll look at that on a spectrum analyzer, but I'll try and point it out as we go along. So if we look here, here's what's now constant. So now n is constant, 2 is constant, and v is still constant. Okay, because we're keeping tension and linear density the same. Okay, so I'm just going to erase those. Maybe I'll move to a highlighter. So when we look at this now, these guys are all constant. So because those are constant, I'm just going to throw them out the door and just focus on the relationship. And the relationship is the length of the string is proportional to the inverse, or 1 over the frequency. So now what that means is if one changes, so let's say if L1 gets longer, okay, Actually, let's go shorter because on a guitar it's going to get shorter usually. So let's say L1 gets shorter. You move your fingers down the frets. So for L1 to get smaller, your F value would have to get larger. Okay, so to keep that balance. So if you imagine your length here went from a 10 to a 1, for that to happen, you would have to have something on the frequency side changing from 1 to 10 or something along that lines. Okay, so you'd have a change in the opposite direction. So I'll show you a quick little video challenge of that, but here's my guitar strings over here. I have a 1 meter long guitar string, let's say, and its frequency is 100 hertz. If I put my finger down halfway, okay, my pictures aren't quite to scale, but let's say that's halfway, okay, what I would find is it plays at 200 hertz frequency. Okay, and if I moved it to a quarter of the wavelength, I would jump up to 400 hertz. Okay, so I have a little video here just to prove that, because as much as I love the math, I also like to test these theories to make sure they're true. And I would totally encourage you to do the same. So I'll end this little video with a short little proof that you can see on a guitar tuner. Okay, I'm going to play the top string here with no fingers on, so it's just wide open. Okay, so you get an F, and you'll notice this is about 87, so I'll do that again. Okay, there's an 87. You will notice there's a couple other peaks in here. Okay, those peaks are the other harmonics. Okay, so now I'm going to put my fingers down exactly halfway. So remember, the first number was 87. I'm now halving the length of the string. You can see about 175 there. So if you take 87 and you double it, it's 174. We were getting 175 on there. There's the inverse relationship we were looking for changing the length of the string.